Hi everyone, thank you for joining me virtually today. My name is Shayen Sreetharan, and the title of my presentation is Prenatal Ionizing Radiation Exposure Effects in C57 Black Mice. So before I jump into my actual research project, I always like to start my presentations with this slide. So as humans, we are exposed to ionizing radiation from a number of different sources. This figure kind of highlights and shows examples of some types of exposures humans may be exposed to. The key takeaway from this figure is that as humans, the majority of our exposures to ionizing radiation are low dose in nature. To get technical, to define what this means, any exposure that is determined to be less than 100 milligray or 100 millisieverts, which are the units for radiation dose, is classified as low dose. This is important because as humans, as I mentioned, almost all exposures that we encounter are low dose in nature. So to kind of extend this, I think it's important to highlight why we are interested in studying low dose radiation effects. This is because, again, as humans, we're exposed to a number of different sources of radiation. This can include exposures from healthcare and medical settings. This can include staff exposures, so for example, x-ray technicians or physicians or healthcare personnel that work close to machines such as x-rays that result in ionizing radiation exposure can receive a small dose. There is also, of course, dose that's given to the patient. This is often done with some kind of benefit in mind. So for example, getting a chest x-ray to look at something for the patient does result in them receiving a slight dose of radiation. Nuclear medicine, radioisotopes, and medical imaging all are categories of exposures that we can see in a medical setting. Another important category of exposures are occupational exposures. So there are a number of different industries where employees and personnel are exposed to radiation as a part of their job. Two important areas are the nuclear power sector, as well as the airline industry. And then as the general population, you can also be exposed to ionizing radiation. One important category is natural background radiation. So this is radiation that's just present on that we are exposed to, living on the surface of the planet Earth. This is mainly from cosmic radiation, so radiation that is originating in space that does reach the Earth's surface, as well as terrestrial sources of radiation. So there are radioactive components of the Earth's crust, and that results in a slight dose. So the key is that as members of the general public, we are given an annual dose limit of 1 millisievert. So any exposure that's greater than 1 millisievert requires special planning or special precautions. So kind of getting into more about what my project about. My project looks more about ionizing radiation exposure in the context of pregnancy. Pregnancy presents a unique scenario because now not only are we worried about any potential effects to the mother, but now we also have to care for the unborn baby. We do know that the fetus does have a greater radiation sensitivity, so therefore we are always concerned about protecting the fetus from radiation exposure. As I mentioned at the start of my presentation, I just want to highlight that almost all human exposures are in the low dose range. Again, we've talked about the different types of exposures. So we know that pregnant women are exposed to radiation at very, very low doses. So we have to consider, are there potential effects of this radiation exposure? So this leads into the next aspect of my research, which is developmental programming. So developmental programming has been getting a lot more attention in the recent decades. We now start to understand that pregnancy and the fetal environment during pregnancy can actually influence the baby after birth. So we can define this as persistent changes in offspring that are due to a stress experienced in utero. So prior to birth, these events and stressors can result in changes in the offspring after birth. Basically, the background behind this phenomenon suggests that there may be an oxidative stress or free radical mechanism that's happening at the cellular level. This is important because radiation and ionizing radiation result in something called oxidative stress at the cellular level. So therefore, we were interested in asking, can ionizing radiation exposure in utero, so prior to birth, similarly result in long-term cellular and physiological changes in the offspring after birth. So jumping into the study objectives and design, our research question was asking if exposure of mice to radiation during pregnancy can result in changes in offspring physiology after birth. So we tested radiation at a number of different doses, ranging from 5 milligray all the way up to 1,000 milligray. So again, anything under 100 milligray we can roughly categorize as low doses. So we tested many different doses, both low doses from 0 to 100 milligray, but also some higher doses as well, the 300 and 1,000 milligray doses. The mice were irradiated using a cesium-137 gamma source, and our outcomes of measure were, again, all after birth in the offspring, and we looked at cardiovascular measures, growth, so we measured body weight in the animals, as well as molecular changes, which I'll be getting into. So this is an overview of the study design. I know this figure is a little complicated, but essentially it's just showing that we irradiated the pregnant mothers on day 15 of gestation. For mice, this is towards what would be the equivalent of the third trimester in humans. So they were irradiated fairly late into the gestational period or during pregnancy. All of our testing was, again, done on the offspring, so not the mothers themselves, but the actual offspring that were born to these mothers. And our testing included cardiovascular testing 3 times a week. Body weight was measured weekly to look at growth and how the animals changed in body weight over their life. And then at the end of the study period, we have actually collected tissues that were done or that were used for gene expression testing, which I'll be getting into. So unfortunately today, I can only give you a very, very small snapshot of some of the results that we found during our study, but I'll highlight just a couple. So the first one was that the 1,000 milligray dose caused a smaller body size and reduced heart rate in male offspring. So if we're looking at the figure on the left, we have the body weight on the y-axis and then our different treatments. As you can see indicated by the asterisk, the 1,000 milligray had a lower body weight and it was statistically significant. Similarly, if we're looking at heart rate on the y-axis now, the 1,000 milligray dose had a lower heart rate, again, that was statistically significant at that dose. So again, just to highlight that these results were in the male offspring. Another research area was the molecular changes. So I, again, don't have the time to get into the technical details, but we looked at a number of different changes in genes that are involved in the glucose and insulin signaling pathways in the female offspring. So we wanted to see if this radiation exposure can change at the cellular level changes in gene expression of these various different products that are listed down below. The key takeaway is that all of these different genes are involved in the glucose and insulin signaling pathway. And the main takeaway point is, again, it seems that the 1,000 milligray dose, which is the orange, is the only dose where we start to see statistically significant changes in gene expression. So again, just to quickly summarize, we saw that doses below that 1 gray or the 1,000 milligray dose did not result in significant changes in offspring growth and cardiovascular measures following birth. Similarly, only the 1 gray treatment resulted in changes in body size as well, although these effects were modest. The qPCR testing for the gene expression changes showed, again, minimal changes in gene expression except at that 1 gray dose. So what we seem to see is that doses below 1 gray didn't really change a lot of our study measures, but we are following up with further studies, again, exploring this research question. So before I end, I do have to finish with my acknowledgements. The principal investigators for this work, Dr. Joanna Wilson at McMaster University, where the actual irradiations and testing were done. I also have to acknowledge my supervisors, Dr. T.C. Tai and Doug Borum, who are both based out of NOSM and Laurentian University. I do also have to thank the many members of the Wilson Lab who contributed to this work: Jessica, Lisa, Mary Ellen, Dr. Suji Tharmalingam, Adam, Devin, and Abigail, and our funding partners as well. So thank you for listening today. Unfortunately, I wasn't able to present this in person as I'd like to, but if there are any questions, my email is available on the conference website. Please don't hesitate to reach out to me. Thank you for listening, and have a great day.